Hello guys, welcome to the Self-Help Maths Academy. Now we are going to discuss the things about the Gram-Schmidt process. The Gram-Schmidt process. So Gram-Schmidt process is basically it is a simple algorithm of producing an orthogonal or orthonormal basis for any non-zero subspace of Rn. So this is the simple algorithm, you can say. It's an algorithm for converting the non-orthogonal vectors into the orthogonal, or you can convert it into the orthonormal. Once you convert into orthogonal, you can also convert them by normalizing into orthonormal vectors. Okay, so it's a simple algorithm. So let us understand how do we convert it and what is the algorithm is all about. So say given a basis, say x1 to xp for a subspace for the subspace say W of Rn. Okay, so this is given. Now what we do is we try to convert this non-orthogonal vectors into the orthogonal vectors by using the following algorithm. The first step is taking v1 equal to x1, and then v2 will be equal to x2 minus x2 dot v1 upon v1 dot v1 into v1. So where this v2 is nothing but x2 minus the inner product of x2 and v1, where v1 is nothing but your x1. So the first step is very important, where you are taking the v1 and v1 is nothing but your x1 and the inner product of v1 with v1 into v1. Then similarly when you want v3, it is x3 minus x3 dot v1 upon v1 dot v1 into v1 minus x3 dot v2 upon v2 dot v2 into v2, and so on. If you continue up to say vp, then here you can see it is v3, then it is x3. Vp in the sense you can take it as xp minus xp dot v1 upon v1 dot v1 minus xp dot v2 upon v2 dot v2 into v2. Okay, so this you have to continue. You can see if it is v2 you have stopped at v1, if it is v3 you have stopped at v2, if it is vp one less than that, that is minus xp dot vp minus 1 and vp minus 1 into vp minus 1 into vp minus 1. So this is the algorithm in order to produce the orthogonal basis. So whatever the collections you are observing here, v1 to vp, these are now an orthogonal basis. These are the orthogonal basis for W. So in addition, actually you can see the span, if you consider all these vectors say VP, they are nothing but the span of x1 to say xp. You can take it as up to k. If you take, then this is nothing but it is valid for 1 less than or equal to k, which is less than or equal to p. So in between you can consider any group of vectors they are spanning. The span of these orthogonal vectors is equal to the span of the bases which are given. Okay, so now let us see the example how the Gram-Schmidt process will help to understand and how do we construct by using the orthogonal process. Say for example, to take a specific example, now let W is equal to span of x1 x2, where x1 is given by 360, x2 is given by 1 2 2. So we have to construct an orthogonal basis, say v1 v2. This is for W. So let's see how do we do it. So the first step is let V1 equal to X1. So V1 is equal to X1 means here my X1 is given, that is 360. Because we have given with two vectors, we will get the two orthogonal vectors. Okay. So now the next step is we know that V2 is equal to X2 minus X2 dot V1 upon V1 dot V1 into V1. So here we need X2 dot V1. We need to calculate X dot V1. So X2 is known to us. Here X2 is given and this is your V1. So X2 will be 1, 2, 2 into V1 is your X1 itself. So now we will calculate this. This is 1 into 3 plus 2 into 6 plus 2 into 0. So which is 3 plus 12 plus 0 which is equal to 15. So similarly we want V1 dot V1. So you can calculate V1. V1 dot V1. So V1 dot V1 is nothing but X1 dot X1. So that is, you can see your X1. V1 is 360. This is 9 plus 36 plus 0 which is equal to 45. So therefore your V2 will be equal to, just substituting the value, X2 is 1, 2, 3. Sorry, it is 1, 2, 2. X2 minus X2 dot X1. X2 dot V1 is 15 and V1 dot V1 is 45 into 360. And this will give us 1, 2, 2. So 15 ones are 15 threes are. If I take this, so it is 1, 2, 0. So this is simply 0, 0, 2. So therefore you have got the vectors V1, that is 3, 6, 0, and V2, that is 0, 0, 2. So therefore this collection V1 and V2 are now orthogonal. So we can check with the condition. If I want V1 dot V2, you can consider it is 0 plus 0 plus 0, that is 0. So hence the inner product of them is equal to 0. So we can say that V1 and V2 are the orthogonal vectors. So therefore this is how we can just create the graphs by using the graph process, the vectors which we wanted as the orthogonal one. So let us take another example where we consider now 3 vectors instead of the 4. So another example where let me take x1 as say 1, 1, 1, 1 and x2 as 0, 1, 1, 1 and x3 we take it as 0, 0, 1, 1. Then we say that x1, x2, x3 are clearly linearly independent and we have to construct the orthogonal basis. So the first step, that is v1 equal to x1. So this is nothing but 1, 1, 1, 1. So similarly, v2 will be equal to x2 minus v2 x2 dot v1 upon v1 dot v1 into v1. So here we need to calculate x2 dot v1, that is nothing but x2 transpose into v1. So here we have got x2, that is 0, 1, 1, 1 and your v1 is nothing but x1, so that is 1, 1, 1, 1. Now this is nothing but 0 plus 1, that is 3. Now we also want v1 dot v1, so this is nothing but 1 plus 1 plus 1 plus 1, that is equal to 4. That is v1 dot inner product of v1, that is norm of v1. Now similarly, now the v2 will be equal to, just substituting the values, x2 So here you have to substitute the value x2. x2 is 0, 1, 1, 0, 1, 1, 1 minus 3 by 4. So this is your x2 dot v1 and this is v1 dot v1 into v1, which is equal to 0 minus 3 by 4, 1 minus 3 by 4. So 1 minus 3 by 4, 1 minus 3 by 4. So this is simply minus 3 by 4. So minus 1, 4 minus 1, that is 1 by 4, 1 by 4, 1 by 4. So therefore, we have got v2 vector. So now we have because since we have 3 vectors, we need to calculate v3 also. So v3 is x3 minus x3 dot v1 upon v1 dot v1 into v1 minus x3 dot v2 upon v2 dot v2 into v2 and x3, this is we have got v2 and now we are getting the v3. So this is what the v3 is. Okay, so now let's find the x3 dot v1, that is x3 transpose into v1. So x3 transpose into v1 is here I've got x3 0 0 1 1 and v1 you know that is here 1 1 again. So which is equal to 0 plus 0 plus 1 plus 1, which is equal to 2. And similarly x3 dot v2 is 0 0 1 1 and v2 we have already calculated. This is our v2. This is our v2, that is minus 3 by 4, 1 by 4, 1 by 4, 1 by 4. This is equal to 0 plus 0 plus 1 by 4, 1 by 4, which is equal to 1 by 2, that is 2 by 4. So we also want v2 dot v2. So this is simply minus 3 by 4 into 3 by 4. That is say 1 by 4, 1 by 4, 1 by 4 into minus 3 by 4, 1 by 4, 1 by 4 into 1 by 4. So this is the just 9 by 16, 1 by 16, 1 by 16, 1 by 16. This is 12 by 16, 4 3s are 4, 4 so it is 3 by 4. So you have got all the values. Now you can just substitute in the equation. You get v3 will be equal to 0 0. This is your x3 minus x3 dot v1 we have already calculated. X dot v1 is 2 divided by your v3 x3 v1 dot v1 is there. So v1 dot v1 already we have found, that is 4 into v1 minus x3 dot v2 is 1 by 2 and v2 dot v2 is 3 by 4. We have already found, that is again v2 1 by 4 to 1 by 4. So simplifying this further, here we get 0 0 1 1 and minus, so 2 1s are 2 2s are means you'll be getting here 1 by 2 and so this is 1 by 2 and this is 4 by 3. So here you're getting 2 by 3, that is minus 2 by 3 into minus 3 by 4. Okay. So here this is here you got minus 2 by 3. So 1 by 2 divided by 3 by 4 you have. This will be minus 2 by 3 here. into minus 3 by 4, 1 by 4, 1 by 4, 1 by 4. So when you multiply this, it is again 2 by 3 cancels. So it is just finally you'll be getting here 0 minus 1 by 2 plus 6 by 12. This is 0 minus 1 by 2 minus 2 by 12, 0 minus 1 by 2 minus 2 by 12. So 1. So here it is 1 minus 1 by 2 minus 2 by 12. So you can get calculate it further. You'll be getting here, if you take the LCM, 12 is the LCM. So 2 6 are. So minus 6 plus 6, that is 0 again. So 12 is the LCM, means minus 6 minus 2 is minus 8 by 12, that is minus 2 by 3. And here it is 1 minus 1 by 2. So 12 is the LCM again. If you calculate, it is 1 by 3 and 1 by 3 here. So you have got the vector. This is now V3. You have got the vectors V1, V2, V3. So if we check your V1, you have got it as the vector which is x1 itself, that is 1, 1, 1, 1. And V2 is the vector which you have got is minus 3 by 4, 1 by 4, 1 by 4, 1 by 4. And you got V3 as say 0, minus 2 by 3, 1 by 3 and 1 by 3. So these are the three vectors which are now orthogonal. Okay, orthogonal set of non-zero vectors. So therefore we can say that the non-orthogonal vectors before they were x1, x2, x3. Now by using the Gram-Schmidt process, we are converted them into the orthogonal vectors. So maybe if they ask in further, like say for example, to convert into the orthonormal, then just you have to normalize them by converting v dash will be equal to v upon norm of v, and say this is your v1 dash. If v2 dash will be, you can take it as v2 upon norm v2, and your v3 dash, that is v3 upon norm v3. So just taking the norm, as you know that norm of v1 will be square root of v1 dot v1. So take the norm of this and divide with this vector. So you'll be getting the new vectors. So now this collection v1 dash, v2 dash and v3 dash, they are orthonormal vectors. So here by using the Gram-Schmidt process, we have got the orthogonal vectors. Now by normalizing them, this process is called normalization. So by doing this, we get the orthonormal vectors. So whatever the corresponding vectors we are getting, that is the new vectors v1 dash, v2 dash, v3 dash, they are orthonormal vectors. This is how by using the Gram-Schmidt process, we convert the non-orthogonal vectors into the orthogonal, and by normalizing them further, we can get the orthonormal vectors. So you can just try out the examples and you can convert uh, the just basis into the orthogonal basis by using the Gram-Schmidt process. This is all for in this session, guys. We will see the next concept in the next section. Till then, take care.